Well, good afternoon, everyone. Thank you all for being here. It's pretty exciting to be at our sixth, that's kind of hard to believe, sixth annual SU Research Day. This is where we come together and highlight some of our outstanding faculty and their scholarly activities. So it's meant to be celebratory in nature and also meant to be academic in nature. And so we appreciate all of you being here, students, staff, faculty, everyone. It's a great time to kind of celebrate what we do outside of the classroom as well as the activities that we do that support our faculty and staff and their scholarly activities. For those of you that don't know the voice or the face, I'm Clifton Griffin, Dean of Grad Studies and Research here at SU. Lots of folks in our office have been a part of the logistics of setting this up, so I'm very appreciative of the staff of Grad Studies and Research for all of their activities today and the last few days to get us started. Do want to say thank you to our president, Dr. Chuck White, for making it. I know he's rushed here from a Board of Regents, a thrilling Board of Regents experience, and so we appreciate you being here, Chuck. Thank you very much. Also want to say a big shout out and thanks and appreciation for our interim provost and senior vice president, Dr. Karen Olmstead, huge advocate and supporter of research at all levels from faculty to grad students to undergraduates. So thank you all for being here for sure. So to keep us on time, I'm going to hush, which is the hardest thing I ever do. Our next faculty presenter is from the Henson School of Science and Technology, Department of Geography and Geosciences. Dr. Craig Ramseyer is going to talk to us about future rainfall variability in the Yunque National Forest.
Today I'm going to talk to you about really the most recent research we've been doing in a long line of research that really dates back about 7 years. But what I'll be focusing on today is some new modeling work we've done in the Yunque National Forest, looking at drought in particular, which is sort of an interesting idea to think about drought in a rainforest, but that's exactly what we were kind of tasked to do. And sort of off the top here, I'd like to thank some of my colleagues at the University of Georgia who helped with this research and actively, and the Luquillo LTER, which helped fund part of this research. So to give you some idea of where we're kind of focused, the Luquillo Mountains are in northeast Puerto Rico. If you've ever taken a cruise to Puerto Rico, which is how most people tend to experience Puerto Rico, most people go to El Yunque. It's kind of it's one of their main tourist destinations, and outside of the tourism piece, a lot of the water supply and water resources for the San Juan metro area of over 1 million people is derived out of this small mountain chain, and lots of biodiversity and important biodiversity and species that are specific to this national forest, which make it quite unique. And here you see a picture of sort of the peaks of the Yunque National Forest, and you do get some idea of the change in elevation we're dealing with here. And I also have sort of an animation later that we can kind of get a better appreciation for how difficult of an environment this is to work in. And to kind of give you some background on how we got roped into this, certainly didn't think as a doctoral student that this would be my area of research, as most of us, I think, can attest to. But we had some colleagues at the University of Georgia at the time that were part of this Luquillo LTER project. It's an NSF-funded project. It's been funded since 1974. And they have been actively doing fantastic, groundbreaking tropical forest research there since '74. About 8 years ago, NSF came back and said, okay, you need to mix it up. And so they contacted the climatologists to come in and to give them a better idea of what climate change looked like in the forest. And so that's how we got involved. But some of the research is really fascinating that's gone on there in 45 years. I have here at the bottom of the screen a picture of a walking stick that is unique to the forest, and a freshwater shrimp species that's specific to the forest. They know everything about these species and how they respond to drought, how they respond to extreme rainfall events like hurricanes. But they didn't know how that was changing in the future. And that's kind of where we came in. And what makes this a little bit more complex is because it is a rainforest, these changes in some of these species start showing up after day 3. In other words, we have to be able to model rainfall on the daily time scale for them, which again sort of adds sort of a little bit of complexity. So kind of what we'll be discussing today is this most recent paper that that's in review at a really cool interdisciplinary journal called Science of the Total Environment, which was nice for us because we typically publish in climate journals, but to kind of get into more interdisciplinary journal is really cool. So we are looking at providing reliable future climate change data, in particular on rainfall in the Yunque National Forest, to really infer future research that's going on there. In particular, they want to know about dry days and drought frequency. And again, a lot of this stems from, in 2015, there was a historic drought in Puerto Rico. For example, in the month of May, our research site typically sees like 27, 28 days of rainfall. So most days it rains. They had 3 days of rainfall in May of 2015. And the result was a very different forest after that month, in 1 month of reduced rainfall. When I went to Puerto Rico in 2015, I could only take a shower at 1 o'clock in the afternoon because they turned off the water because of the reduced rainfall in the forest. So this is, while we're focused more on the ecology here, this does have sort of political and economic results as well. So the last piece is to provide some estimate of change in total precipitation. We didn't think we actually could do that, but I'll show you, we kind of got a nice surprise. It doesn't happen very often that you get to do a little bit more than you thought you were going to be able to, but we did in this particular study, and so I'll show those results as well. We are doing something called climate downscaling, and you know, if you take nothing else away from my talk, I hope this does provide you sort of an example of what type of research is going on in climate science right now and how we are looking at climate change. And so climate downscaling is kind of the newest way of answering a lot of these questions. And so we're downscaling precipitation data for the future out to 2100 to a single point on the Earth's surface. And that location is the Verde Field Station. It's about 380 meters above sea level in the Yunque National Forest. We picked this site. This is kind of our home base for a lot of the research that goes on in LTER. And so obviously they have 45 years of good data there. Good, relatively speaking. The tropics are notorious for not having great data, but as good as you can get in the Caribbean. And the way we do this and the way we went about this was using something called an artificial neural network. Artificial neural networks are good at modeling nonlinear data, which rainfall certainly is, and I'll speak to that in a second. And so these are very flexible models that take large-scale atmospheric predictor variables. Just as an example, and I'll show you more in a second, you know, obviously moisture is a big predictor of rainfall. In the summertime, when it does rain, it rains heavier. We have more moisture available to us versus a winter rainfall. That's just one example of the predictor variables that went into here. And at the output here, we're ending up with some sort of precipitation metric. This is the same sort of modeling, for example, that's used for image classification or facial recognition software. It's really good and flexible at picking up on patterns, and certainly rainfall does have sort of patterns that we see in the atmosphere that are related to rainfall. So we ended up with 9 inputs, and then again it goes through a couple of a couple of layers of what are called nodes, and we get this output here. And so we're taking the large scale flow of the atmosphere and downscaling it to a point on the Earth's surface. I've put together a little, because I am trained as a geographer as well, I had to put some sort of map in here. But basically what we're trying to do is, 100 years ago, we started investigating greenhouse gases and their impact on temperature, global temperature. And after we sort of got a good handle on that, we started to build global climate models that were able to differentiate between the tropics and the poles, for example, and tell us what temperature looks like, for example, in this part of the world. And that's really where we are today with our climate models. They treat this as a homogeneous space, okay? And there's a lot of reasons for that. But that's not good enough. We know Puerto Rico is very different. San Juan is very different than El Verde Field Station, for example, in terms of the rainfall they receive. And so our task is to downscale this large-scale flow in the atmosphere to right there. And that's where the El Verde Field Station is. I particularly like this imagery we have off. It may be hard to see, but a lot of the stuff is brown here because this was taken shortly after Hurricane Maria. And then we're going to slide down to sea level here, and we'll look back on our field station so that you can get some appreciation for kind of the topography again. In an environment that is this humid, if you go up 100 meters of elevation, you're going to drastically increase the amount of precipitation, right? And so as we go up to 200 to 300, so there are very different amounts of precipitation 100 yards away from here. We have rain gauges that close together that show us very different things because of this change in elevation. So more specifically, what we're doing is we needed to compile a suite of 4 global climate models and those predictor variables in particular, and we'll look at them in a second. And we take their historical runs. So we run the global climate models backwards in time as well. And the reason we do that is for verification, validation. How well do they handle the past? And we find that they do pretty well. Some variables better than others. They're better at temperature, for example, than moisture in the tropics. But we bias correct them, right? We know what their biases are. We correct for them, and then we update their future runs, which are the most important piece of data we have, so that we're accounting for the biases that exist. Typically, most climate change downscaling studies that you'll find, we tend to look at 2 scenarios. We look at a mid-century scenario and an in-century scenario. And we do that largely to look at sort of the trend, how do things tend to be tracking over time. But also, as you're going to see in a second, this is not going to necessarily be linear. Some of these changes may occur quite rapidly, and then we may see some sort of a recovery, and that's actually what we find in our research. So, to give you some idea of this change in precipitation we have in the forest, the bottom, the yellow that you see on this graphic is from the San Juan Airport. That's their daily precipitation. If you go up to our site, which is this blue, the blue line, we only changed, this is about, direct line of sight about 11 miles away. And you can see that, for example, in the wettest parts of the year, in May, for example, we get about 6 millimeters of rainfall per day at the airport, and we get about 14 up at our field station. So what's happening in San Juan, right, is not representative of our forest, even though it's 10 miles away. And global climate models treat them as the same thing, and that's really the issue that we have. And then if you go up to the very top of the mountain, right, that's about 1,000 meters, you see even further increased precipitation. And so my study that we'll look at here is really focused on these 4 months, April through July. We call it the early rainfall season in Puerto Rico. They have really 3 rainfall seasons. There's a dry season that sort of starts in December and terminates in March. And then what's called a late rainfall season that really begins in earnest in August. August, September, October is organized tropical storm season. That's when we get lots of hurricanes. They're low frequency. They're very hard to model. But more importantly, why we focused on the early rainfall season is we found in a paper that's in review at Weather and Forecasting we found that the early rainfall season drives the annual variability. In other words, if we're going to have a dry year at our field station, it's going to be because the early rainfall season was dry, right? If we have a wet year, it's because the early rainfall season was likely wet, unless you bring in something like Hurricane Maria, which is obviously a sort of a deal breaker, okay? So that's why we focus on the early rainfall season. It's really what's driving the annual variability at our site. We trained our neural network with about 3,000 days. That's the maximum really we had available to us. Neural networks, like most models, the more you feed it, the better the predictive capacity. And here what we found was after several different iterations of running the model in different architectures, we developed a model that predicted wet days and dry days at our field station with 92% accuracy through the historical period. In our line of work, that's pretty good. And so the other thing that we liked about this particular model, the red is where we had errors, and you'll see that the errors are evenly distributed, which was a good sign. There was no sort of skew in the errors. So we ended up with a model we liked, and thus we finally moved forward after probably 8 months of sort of test bedding different models. Neural networks are thought of as a black box, which means that most people don't think you can see into them, to what they're actually doing. And there is some truth to that. However, there are techniques that actually came out of the biology field, which is very interesting, to actually go in and look at the model in detail to figure out which of these predictor variables are sort of most influential in the output. And so we know, for example, specific humidity is a measure of moisture, all right? We established, as several people have in our past couple of publications, that these are very important predictors of precipitation, especially moisture near the surface up to about 10 to 12,000 feet. So these different specific humidities you see are obviously very important in the model. If you don't have enough moisture, you're not going to get rainfall. We have another metric here that another paper that we just came out with shows that vertical changes in wind direction actually have a big predictor of how efficient thunderstorm activity is going to be. Okay, and so we threw that into the model, and then these four guys down here are purely what we call a thermodynamic index, looking at the thermodynamic potential of the atmosphere. In other words, how likely are we to get a thunderstorm? Okay, so when we ran this and we peered into our model, we see that all of these have some importance in the model. Previous iterations of this, we had variables in here that had like 1%, and we took them out to simplify the model the most we could, okay? So what we found was, and again, this is an attempt to really show you the importance of thinking about this non-linearly. The thunderstorm potential index, this GDI up here at the top. Oh, my thing died. Oh, that's a bummer. I just put the new batteries in there. Okay. Hey, let's see if this one's working. No. Okay. Top line, GDI, is the thunderstorm potential. You'll notice that from the historical period to the end century, that value decreases. It becomes negative. I put an arrow down indicating to you that we know that to be obviously bad for rainfall. There's an inversion term, and for the purposes of this discussion, the inversion is really a limiter of thunderstorm potential. And as that value gets more negative, again, the potential for thunderstorms actually goes down. So far we've got two downs. What we see over time with moisture, however, is that we see an increase from the historical to the mid-century, and then an even actually bigger increase towards the end century. That's actually because of increasing sea surface temperatures. As you increase sea surface temperatures, you increase evaporation and put more moisture into the atmosphere. So that's actually good for rainfall, right? And then the last piece here is that we have increasing wind shear in the atmosphere. Increasing wind shear is bad for rainfall at our site. So we have some knowledge of what to expect, but we have differing signals here, and we need to sort of sort that out. What we found was that by mid-century, and this is really, I think, the most important finding we have, is that by mid-century, we see a 10% increase in dry day frequency. Most of the planning that is going on in Puerto Rico for climate change is really targeting the in-century. Previous research with using global climate models suggests that that's when the most serious changes will occur. If our study shows that these changes are actually going to occur much more rapidly than that, right? This is 20 years out now. 2041 to 2060, we'll have a 10% increase in dry day frequency, which is going to lead to more drought and longer dry spells. However, by the end century, our models are suggesting that we actually get a decrease in dry day frequency back towards present day. So essentially, we have to ride out the next 40 or 50 years, and the atmospheres, because of that additional moisture that we're going to get, it does flip the signal, which is really interesting. And all this does here, so the pink is the historical value for April, right? You get about 65% or so. You see the increase up to the mid-70s. The gray bars are just all those individual different models that we looked at. We're just taking what we call the ensemble mean. What's the average of all of these models? And that's, nowadays, any climate change research, you have to use multiple models. They have different biases, and we have to account for all of those. We also found out, and this is kind of the cool thing that we got to do that we weren't expecting, was we just happened one afternoon, me and one of the co-authors, like, well, let's just see if there's a relationship between how many dry days we get and the total amount of precipitation for the season. And what we actually found was, and I'll just focus down here as we're running out of time, is that when we take just the seasons where we have great reliable data, we have very little missing data. That's what the less than 10% means. The seasons where we have lots of available data, the relationship between number of dry days and precipitation is about 0.95 R-squared. And again, in our line of work, right, I'll never see that value again, right? We were very ecstatic to find this relationship. So what it allowed us to do in closing here is derive that relationship and look at how the dry days, which again increase pretty dramatically between now and 20 to 40 years from now with a recovery at the end century, right, which is also going to lead to longer dry spells, which is really, from the ecological standpoint, is what they were most worried about when we presented this work to them. But we also see, because of that linear relationship that we set up, that there's about a 200 to 250 millimeter decrease in rainfall between now and 20 to 40 years. This will have dramatic impacts on water supply. This will have dramatic impacts on forest composition, and really emphasizes the urgency that the folks in Puerto Rico need to have now moving forward to adapt to this. Hurricane Maria did not help. My colleagues in Puerto Rico assure me that it'll be 20 years before they recover from that hurricane. And so that's certainly a source of uncertainty that's been thrown into the equation now. So in closing, short-term droughts likely to increase by mid-century. Really devastating impacts on the forest are possible in a very short time period. And one of my colleagues from Puerto Rico, I think, said it best, what's going to be left over by the time the trend reverses is kind of a really important thing for us to think about. If we can gut it out to 2060, we may see some recovery, but they really question what's left, even in that short time period. So I want to thank you guys for hosting, and again, I got a few citations up there, but I'd be happy to answer any questions. Thank you.
It's sad, but good, right?
That's a very appropriate way to describe it, yes.
So how applicable is the work that you're doing to other tropical forest areas? So could the work you do in Puerto Rico also, affect predictions in Central America as you kind of go down and into South America?
Yes, I mean, it's a good question, and we feel very confident that what we've found probably translates really well to other islands in the Eastern Caribbean, for example, we have very similar climate regimes, and we've even done some preliminary modeling to sort of show that. Once you get into Central America, you do see slightly different forcing mechanisms on rainfall. Now, we could certainly try our model, but typically in our line of research, you would actually tune the model and adapt it for Central America as well. That's really, it's a lot of work, but it's really the way that we do climate change research now is to be as specific as we possibly can to the location, because it does differ over such a small period. The model that I developed for the San Juan Airport, which we didn't end up publishing, we're going to basically do a lot more of these models and publish them in bulk, but the San Juan model does look slightly different than the El Verde one. There's differences in the importance of different predictors, actually, even 10 miles away.
So just to follow up.
Yeah.
So how do the species level? So do you ever kind of include the biology part of it, right? So
Yep.
whether it's a frog or,
Yeah.
or a bird species.
Sure. There are so many different levels of research that go on in the forest. I've heard the same story from one of my colleagues from the University of Georgia. He's an ecologist. He works on freshwater shrimp, right? And one stream. His whole career is one stream. But he knows everything about them, right? And he knows that on, I think it was day 5 or day 6, the shrimp actually start moving upstream during a drought to find, I don't understand the lingo at all, but basically there's more nutrients upstream at the headwaters, and so they track the shrimp upstream. Those are the types of research that they've been doing for 40 years, but they just actually never understood, well, how frequent is drought, and how frequent is it going to be in the future? And now they're starting to get a better idea. And I mentioned here as well, Hurricane Maria kind of threw a wrench in the future plans of the project. We were all in on the drought stuff because 2015 was a big drought, and now we seem to be like, we may have to start modeling hurricanes now because of the devastation that we just saw. We actually didn't have access to the field station for about 4.5 months. There's one road up there, Puerto Rico 186. They opened it for 2 weeks, and then there was a landslide, and it's closed for another 3 months. So just devastation. In fact, I showed my students a picture of the forest after Maria, and I took a poll. I said, who knows what forest this is? And they had multiple choice. Unequivocally, it was 100% said it was the Appalachian Mountains. And it was this tropical rainforest that was completely devastated. So a little shift probably likely, but thank you for your question.
One more question?
Sure.
So where we work in Panama, we have these El Nino events that generate droughts. So you were mentioning that warmer sea surface temperatures generate more moisture. So for the climate science literate among us, can you explain how these El Nino events create droughts in certain areas?
Sure. So, El Nino has a different signal in different parts of the world. In fact, research in Puerto Rico shows, and I'm glad you actually brought this up, the research in Puerto Rico shows that El Nino has very little correlation with any hydroclimatic metric in Puerto Rico. And so some places it matters a lot, and some places it doesn't. But El Nino is not just an addition of moisture, it's actually a dispersion of low and high pressure systems, for example, and where you have sinking in the atmosphere and where you have rising in the atmosphere. So in that context, you're basically shifting where a lot of these motions are. I spend, some of my kids from my tropical meteorology class are here. I think I spent 3 weeks on El Nino because of how different the impacts are depending on where you are. And so we really trace it from its origins, which is in the Pacific Ocean, downstream. And the research shows that some places there is a good sort of signal between El Nino and some places there aren't. And at our site, 2015 was blamed on El Nino in the media, and it was blamed, and even my colleagues that are ecologists, the El Nino is driving the drought. And we were like, no, that's, it was in USA Today too, right? They were and so we went in and did some research that showed, for example, the 2015 drought in Puerto Rico is actually driven by Saharan dust, right? And so sarin dust plays a big role in the Eastern Caribbean and dries it out and stabilizes the atmosphere and all kinds of fun stuff. So, we could talk about El Nino for a while, but it's really dependent on the place in terms of what kind of impacts you'd see from it. But it certainly is nonlinear. When it's El Nino, it's not necessarily going to get wetter everywhere, for sure, right? Thank you. We good? Thanks.
Thank you very much to all of our faculty presenters. We certainly appreciate your energy. This brings us to the end of our faculty presentation part of the SU Research Day. We encourage you to stick around, have some refreshments, and visit with the folks that are in the back. Once again, thank you to all of our faculty. Let's give them another round of applause. Fascinating array of scholarship that we heard about this afternoon, and it always is really a great opportunity to hear from our faculty. Thank you so much.